Actually got a mic, so you can turn off the mic thing. Looks like it will be working. So you can see the little microphone. It should. Mm, sort of channel. No, that's not the button I was looking for. That's the button I was looking for. Oh, this shit doesn't have it. This. Let's try. Shape. Yeah. Mention. Mm. Om vi sätter den här bara nyfikenhet, så låter det då. De börjar bajsa skiten. Den är så fucking efter sig. Svårt att höra. Jag vet inte om det är något konstigt i ljudmixen på... Okej, good enough. Yeah, I guess att den stör mig tillräckligt mycket på den, så får jag helt enkelt bara byta. Så vi ska se om jag tar ner den och... Jaha. Matlab. Bra. Så. Stanna på att den inte så. Vad händer? Det försvinner. Nej, okej. Nej. Så vart tar den vägen här? Current ska den här på. Jaha. Stupid. Så, sånt här. Så jag kommer ihåg det sen. 17. 61, jag tror inte jag kommer glömma. 45 helvete. Då kommer den bara till 21. Not so much. That's really good idea for det to be up. Alright. Ja. Vi ser väl vad vi kan göra här då helt enkelt. Så då. Edit on the script. Code output and format the text in the single executable. I think I'm good for now. Lagar den på här warning found. I don't know what any of this means. Syns man idag. Vad som är lite småsmutsigt igen. Flyger mobilen fine. Den stänger vi. Stänger dem där. Stänger. The file looks current ML's pictures as the current signal, which was measured when a transformer was started. Download the dataset here. The signal was a sampling interval for 1 millisecond. One would expect that the signal should contain several harmonics of 50 Hz base frequency. Precis. På grund av bakgrunds eluttag och sånt. This is ever not seen using the default parameters of the SPA command. Find better parameters M and W for the command phi equals SPA where phi estimates the spectral density C dot E. Use the spectrum plot command. Vi borde se här. Lite olika figurer här. Input output data. Covariance function. Auto correlation. That's event information house. So this doesn't do. So I would suspect that the signal would contain several harmonics of the 50 Hz base frequency. Find better parameters M and W for the command. Jag sitter ju men den används ju inte. Den är avstängd. Det var alltså bara... Vad används bara? Den används för dessa ställena. Ja. Av Z medans här... Jag är lite förvirrad över vad... Så för att de ville plotta den här. Jag tycker det var så konstigt varför den var utkommenterad. Så här ut som jag gjorde innan. Så som ett sånt som också vill ha. Nyfiken bara på hur... I'm just making sure så att jag har fattat vad den här till för. Så att säga. Series sampling interval of 1 millisecond. One would expect in the console. Present in the default SPA component. Find the parameters M and W. Matlab spa. Set the window size and frequency. And a window. Okay, this stuff. Estimated spectral density. Contains the output Y and input U from an experiment. Number of lags in impulse response. Number of lags. Frequency vector. Spectrum. Right, så att den där är inte inne. Matlab. Okay. It's a fun conversation. Oh, there's oh, this is showing. Visst är det här. Plot options. Så man trycker här någonstans. Open spectrum plot. There's a lot of information here. Let's see if we can get help on spectrum plot. Does that bring up what I'm trying to? Yeah, this is what I wanted. Open the browser. Come on, we open up in the browser. Why is it so goddamn slow? I'm fairly slow too, so I'm not gonna be an enormous hater. Alright, let's see. So how are we using it here? So we're getting it and then we're plot options. We're using this version. And it just gives us a nice thing. So that it should be the last figure, this guy here. Which makes sense, because this is what we yeah. So the power to the frequency. This makes sense. It's a bunch of other options we have checked. That does make sense. That does make sense. That does make sense. I don't know if having the microphone here, like, it makes the audio any good. Now I'm speaking more. It should probably be like here. Just slight. In. It's very much in my field of view when it's down here, which is fairly annoying. I sit up straight, like I should be. Looking at here, it's not quite as much in the way, at least in theory. Hopefully the audio is fine. Right, so we're gonna change M, which was oh, I shouldn't be as tired. Goddamn, to spa here. The data, which is said, which is calculator from the input minus the output, I think. Which was in the thing here, which here it takes like the mean I for R. I don't know what I for R means. No, I for R, is it like variable type of double? No. Oh, because it's in current, right? Yeah, because if you check current, you have a thing for it in here. I for R, yeah. So it just loads the data, which is our. I'm not sure what it means, but that I for R would stand for. But that's beside the point mostly. There were TS, we were Y, so this all makes sense in some ways. There is a clear periodic behavior with a significant correlation even after 400 samples. The signal has a non-zero mean, so we remove that before applying COF. We check that the covariance of Y is correctly estimated. Right, because in the first image we see here, so after 0.4, we still definitely have harmonic things. There is a non-zero average, there's an offset. So these are things that we want to take care of. So this is what's comment here. This is a great comment that they've added here, right? That's the reason why they show this. So we need to take away the mean, which is done somewhere. Just trying to figure that out. So in the second plot here, what are we seeing here? I just need to make sure that the covariance function, the autocorrelation, the neural lag. So what it said here, we were Y mean. Where is Y mean used? Y mean. It's not used anywhere, which is weird to me. Because it says here that we're doing stuff with it, but it's not actually used. That seems a little weird to me. But return also is weird. Covariance function of said 500. What is this 400 here again? It's the amount of, it's not amount of data points. I mean, I am. I'm looking into covariance compute. Physical variance function estimated for a data matrix. It's obsolete. Use CRA instead. Alright, we're using obsolete functions. It is what it is. We'll let it be. We will let it be for now. I just wanted to know what 500 meant. Oh, it's the lag, right? So how long do you want this to go on, so to speak? Because here it goes to 0.6 seconds, and this is then in milliseconds. Yes, it's 500 milliseconds. Yeah. So it doesn't go to the end, which is fine. It doesn't really matter. And you go so plot 211, which gets you this format here, I think. And then you plot R, which is the covariance function. So this is then the covariance function. It's like, remind me, what does the covariance function do in this matlab code? That is Cofunction matlab estimates the covariance function of a time sequence signal. Let's break it down. Represent specific context. Function overview. Perhaps the cofunction computes the covariance function Rk of the time series. Different lags k equal correspond to covariance of specific function. Breaks this down. Variance check. What does a covariance function do? The covariance function quantifies the relationship between a signal's value at a different point in time. It's 2 points in a time and linearly related. I mean, it's good that I'm getting a crash course here. I mean, let's see if we open up. No, it is from this thing. So if we open up here, you know, I'm totally thing. Covariance function estimation. Same covariance function spectral density. This is lecture 10. If we open lecture 9, I'm just really like, yeah, these things are a little hard to understand. These lectures were a little hard on me. Reverse junction, reverse nation, the erection max. I should probably read through. Do we not talk about covariance in this thing? Getting a little tired. It's too long though. So it should be fake. It should be considered fake tiredness. Not done anything today to deserve to be decided. I went to the gym. My heart pump. Yeah, I feel like I need a fucking YouTube video. Hey, look, it's me. Covariance. All right, now my brain is sort of getting.
Hello, people from the future. Welcome to Normalized Nerd. In this video, I want to talk about covariance. But why should you learn this? Well, first of all, covariance is inevitable. Well, that I will explain in some other video.
So here's my picture. This is a funny shape. Even okay, there's an angle where there's a little bit more light. I put the light in a bad position, I think. It's very dark. But you see that this is a joint Gaussian distribution, and it is somehow has a funny flat shape. Or we also see there's some correlation. And well, why is that so? Because I used a covariance function that gently decayed with distance. So it means my point x1 is positively correlated with x2. And it's a little bit correlated with x3 because x3 is further away.
är Telia.
Halva priset under hela Black Week. Det är Telia.
How do I get smarter? Like this. Brilliant is a universe.
Hi everyone, welcome back to Prakasham tables. And what are the two samples?
Right. Yeah. I was just confused about the. I realize now why I was confused. So the covariance between. So take the covariance of the points. Covariance of a time series. Is that a concept that like makes sense in my head? Because taking covariance between so the distance away from the average mean. So I guess the calculation here is y mean. We don't give it. I mean the code. This fucking thing just calculates that out itself. So when finding the covariance, covariance. Function. Yeah. So you have your specific, minus the expected value of said, given both of them. So it's the covariance in both directions. So it's the covariance in both directions. So what the spread of the data, how spread out is the specific data point in comparison to the other. Well, the first the covariance describes how much a random variable changes. How much two random variables change together with varying spatial and temporal separation. Yeah. So this all makes, I don't know why my brain decided to forget what this meant. All right, like I just needed to read it a bit to like fucking like jog my brain into like remembering what the words meant. What does it mean for it to be autocorrelated? Shit. So let's read through its answer here. Life table with k is mu, where mu is the mean of the thing, yeah. So we have the covariance RK for a discrete time signal, which we have. It's underneath it all. It's a discrete time signal because we're sampling it at a certain rate. Is defined according to this. So the covariance of the two time steps or the two time the two values for the different points in time where we're stepping 1k, one step size towards the one time shift with the lag is equal to the expected value of so the difference between the signal at time t and the mean value of it times the average distance or the distance between our current point in time divided by our minus the average times the point in time one step forward minus the average. Take those time each other. Take the expected value of that number. If I'm reading it correctly, yes. And that's your covariance. That makes sense because that is how you calculate covariance, and we're calculating the covariance between those 2 points. So this all makes sense to me. And if they were uncorrelated, right? So if you take covariance, we take the Wikipedia here, and if we type uncorrelated, I'm curious about what autocorrelation means. On a serial correlation, the discrete time case is the correlation of a signal with delayed copy of itself as a function of delay. Informally, it is the similarity between observations of a random variable as a function of the time lag between them. So, wait, let me read through that. Let me read that again, see if that made sense to me. The autocorrelation, sometimes known as the serial correlation in the discrete time case, is the correlation of a signal with a delayed copy of itself. Let me YouTube autocorrelation.
There's really no better time than now to take your productivity to the next level. Grammarly is offering 50% off all Grammarly Pro plans for a limited time. I have a habit of writing run-on sentences that aren't the easiest to follow, but with Grammarly Pro's Clarity Full Sentence Rewrite feature, Grammarly not only identifies those run-on sentences, but also rewrites them for me.
Autocorrelation is one of the most useful tools for time series analysis, and in this video I'm going to explain to you what autocorrelation is, why it's important, and how we can use it in Python. So let's get into it. On the screen now is a notebook that we're going to work through that's going to give us the ins and outs of autocorrelation and how we can apply it in Python. So let's first start with basically kind of the main reasoning behind autocorrelation. So in time series analysis, what we're after is about try to analyze our data so that we can make accurate forecasts for the future, because it's used in businesses, which I discussed before, and it's a very useful concept forecasting to have in any industry you're in. Now, to be able to forecast effectively, we need to be able to understand our time series and be able to diagnose it. And one way to diagnose it is through autocorrelation. So as I've written here, autocorrelation allows us to decide what features to add to our forecasting model. This is particularly important when we go to things like ARIMA models, we'll discuss in a later video. But autocorrelation is a critical tool when working out which features to add to the ARIMA model. Again, we'll discuss this in a later on video, but this is going to be the groundwork, and also there's some other important parts of autocorrelation that we need to understand. So let's now talk about what autocorrelation is. So autocorrelation is just the correlation of a time series with itself, but at different lags. Now, as I've written here, correlation is just a measure of how strongly two variables are related to each other. So if the value is 1, if the correlation between two values is 1, that means they're perfectly positively correlated. So when one variable goes up, the other one goes up by the by the same or linear amount as the other one went up by.
Let's turn this on again. So we're correlating. Yeah, so we're correlating the series with itself a little bit further on in time. So what does that tell us? If we look at the graph, so the autocorrelation here, right now the covariance function and autocorrelation are they the exact same? What would it mean for them to be the exact same? That feels like that would be wrong. Okay, the spectrum estimating. The spectrum is not well estimating using the default value phi, which is here, which is the spectrum analysis. SPAV said phi of these things. Because here we're just plotting this. So if we do these other guys, and then here it should say phi 100, phi 200, and phi 300, and we run it. Oh, it's called phi 600. Armor dummy. Phi 600. One section. Right, because we need hold on, I think it's called. And then okay. So now we have multiples here. So here we have the phi with the different. So with m here we have 100. Try different values there. Yeah, phi. He should be named phi m really. Phi m. Is that right? Oops, whatever. Phi m. Yeah. So now we run it here. Okay, so maybe we don't need all of them. Let's remove these two for now. This and this. Now we run it. Oh wait, because that thing is on. Right, of course not. So here now we have just the two. Yeah, so it is dog shit at fire equals 100. Fire is 100. So M was. Yeah, I can say it like this. It looks a little silly, but. And definitely close up this thing. That's not what I wanted. That's not the home, maybe. Scroll. This one. So M is the number of lag in impulse response. Number of lags is. So is that the number of lags feels like a weird way of saying it. So if I understand it, it should be the amount of time delay. So lower number should be better, or should be something. Let's give that a shot. Let's see what happens. Better, which makes sense. We would expect it to be better for lower numbers, if I'm understanding it correctly, which I might not be. If we now put it at like 550, it's the amount of lag. No, because now it's worse than it was at 100. At 30. Now it's close there because it's very small. Which makes sense if we zoom in. Right, like now it's very, very close because now we're not going very, very far, so to speak. So we're using like more compute power, right? That would be the case, which makes sense. So we're using fewer number of lags. Number of lags feels like a weird word to use for it. Can I like mute apps? I fucking hate getting notifications from maps. So let's see if I can do that. I'm very, very tired tonight. Trying to see here where to do that. Maybe I'll need to search for half or so of sense. Can be nothing to ever. I don't think those guys have a name. I don't know. That's a good one to have. I want from this guy, sure. Sure. I want from this guy. Not from that guy, whatever, don't care. That's fine, sure. So what word do I get from Uber, right? So that's one I want. Um, right, because if you're actually getting a car, you would want the notification for it, so to speak. It's actually a little complicated. Yeah. The frequency vector of which phi should be estimated. The frequency vector for which phi should be estimated. So VW is a linspace here of point TS. TS is a concentration of fun. The spectrum 0.005, this is the time step. So pi divided by time, because right, because we're going from there to. Wait, why? Why is that our linspace frequency vector for which is an NW number of frequency points? Huh. Number of frequency points. Yeah, sure. Is there a certain reason why that's divisible by 2? Or I should say multiple by 2. Maybe. Is it something to do with the pi? Oh, fuck. Oh, I don't know. Sorting spectrum, yeah. So now this guy's better. So it makes sense. Lower amps would produce a better result. Worse amps would result in or like longer amps to taking more lag, which maybe we would need in like a real world situation. Mm. Estimated spectral density. If we where's the snip? Am I fucking blind? He should be here somewhere. Maybe it was. For the matlab SPA command, is it not just better to use lower m? Since it samples more often? What does changing the m variable mean? Right? In MATLAB spot command, the parameter m is the number of lags used in the impulse response application for the frequency resolution. Determine the length of the window used for averaging. Yeah, all right, you're right, right. Yeah, 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 yes, yeah, 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 yes. It's all coming back to me now. Yeah, yeah, yeah. So if you have a lot of noise, you're gonna need a higher M. But if you have a very clean feed, you can have a lower M. Increase frequency resolution, ability to distinguish close spaced frequency. Reduces the variance of the spectrum, making the results smoother. Exactly. Why not always use small m? Because it reduces frequency resolution. Closest between components may not be distinguishable. So if we check our thing here somewhere, around 50 hertz, go out here. Here we have a spike. Look, this is what we were looking after. This all makes sense. This is exactly what we're expecting. That's not what we were expecting. Oh no. Frick. Go back. 50 hertz. Here, wait, we're seeing a thing. Huh? Okay. Uh, so if we allow these things, it definitely shouldn't be seen. Should be. I mean, well. No, wait, these guys get it. So it was too small. Right. Okay. So it's it is noticing it though. I'm a little confused. So what's the default phi? It's phi n. Just spectrum analysis. So this takes the estimate the frequency response. Decent spectrum analysis. I'm learning a lot. Because it's not like there is a bump. Because in the question it says that there isn't, but there is. Why would I suspect the signal should contain several harmonics? I guess that is considered one harmonic. Because here okay. Sure, because here we see the wobbly bits, which is what we're expecting. Is my mic on? My mic is on. Good, as just check. Yeah. Here we see several harmonics at that's gotta be 600. So there we are including more. So here it's smoothing them out. Fine frequency resolution is critical. Increase frequency resolution. So I'm thinking about it in the wrong way. M determines the length of the window used for the averaging. Large M's reduces variances to make the result smoother. Doesn't it's this? No. Yeah, I mean it's doing what it's doing there because it's increasing the frequency resolution, so we can see these frequencies, which we can't do for the lower M's. So that makes sense, or it makes sense with what it's saying here. Didn't initially like click in my brain. This is what it like meant. Like just the number of length. If you have more, it should be smoother in my brain because you're averaging over more points. Mental model am I going on here? I don't think I understand why the frequency resolution would be higher when m is larger. In my mind, we are averaging over more points. That should reduce the resolution. But this is wrong. I spelled resolution wrong. I hope that it gets. Your confusion is entirely understand. Let's clarify your mental model and frequency resolution in this concept. The key lies in recognizing how window size m, frequency resolution versus variance. So it should reduce variance, but it looks like it increases variance. You're thinking that increasing m reduces resolution because it seems like we're smoothing over more data, effectively blurring the details. This intuition is valid in certain but not here. The resolution in the frequency domain, the ability to increase a little bit, improves the ability to separate them because a longer window in time. But why does it mean that? In the mathematics of the Fourier transform, so the delta f, t is the total window duration. It's 1 over t. Ts is the sampling interval. That one is a constant. We know that. It's 0.001, I think. It's in the variables over here. Ts, 0.003, yeah, millisecond. That one is constant. We can change the amount of them we take, which makes that number down there larger, which means that zooming into the longer observation time, the more details you can distinguish. I think that physical analogy is stupid. Shorter observation time gives a coarse view where closest by details may merge. I think the physical analogy is retarded. But this part here is helpful. So it has to do with the Fourier transform. Why it's moving isn't the same as reduced resolution. Averaging over more lags reduces the variance of the spectral estimation, making it appear smoother. However, the smoothing affects noise, not resolution. That's key. The resolution depends on how well the method separates different frequency components, which improves with larger n's. Improved frequency resolution reduces variance, requires more data, and may miss transient features. Why does that miss transient features? It reduces the resolution with smaller m, captures transient rapidly changing features. Right, so it captures more shit in right, because the difference here is here we're in the frequency domain. What I'm thinking about is the time domain. Now that's clicking. That does make sense. Yeah. So we're increasing our span in the frequency domain, so to speak, not in the time. Not in time. or something. Changing the melody. The physical analogy seems fucking retarded, but I'm understanding things. My brain is cooked. I have slept very little today, and I over caffeinated like a motherfucker in the morning. Um, I'm crashing a little bit, but I am not. I'm expecting myself to sit there for about another hour, and then I'm going to do some cleaning. Download vibrations.math containing two experiments of a mechanical system having several vibrational modes. Import data CH into the GUI. I think there's a video of the GUI. I should watch that video. I really should. I should actually learn the thing. Alright. Yeah. Should learn the commands too, but should probably use the GUI first. Right, because I never watched that fucking video. I kind of forgot about it because I was doing other shit. So I should go find that video. It's like 40 minutes long. I should track my way through it. Probably shouldn't sit this close to the mic, actually. Probably focus the audio a little. I know it should be close to the mic, but you shouldn't be this close to the mic, right? Like there's some sort of optimal distance away. Oh, I shouldn't breathe into the mic like that as well. It's a really bad idea. Yeah, I should take the time to do that. So I'm gonna turn the stream off because watching that video on stream will be dumb. So I'll do that chat. Thank you guys for spending this hour with me. We learned about the first thing. It took an hour to do. That's kind of embarrassing. It is what it is. I learned a lot, right? Because fundamentally, I'm standing on a bit of a weak house of cards. So we secured a little bit of a foundation here, right? I mean, my brain is not operating on the highest level at the moment, which is fine. So we're all good. I'm gonna watch that video, attempt the second one here, and then I'm gonna do the dish. Well, I have dishes to do as well, but I'm gonna do laundry and dishes and try and make this place a little nicer for the weekend and such. So that's the goal for the rest of the day. I might come back stream later. We'll see. We'll see. Yeah.